4 students and 5 students.
Okay, so hello everybody, and thank you for coming to the seminar. Let me begin by acknowledging the true and traditional owners of the land that we are currently gathering and paying my respects to their past, present, and future generations, Gadigal people of the Eora Nation. Today we have Dr. Claudio Roncoli. Claudio is an associate professor at Aalto University. He obtained his PhD in transport engineering from the University of Genova 10 years ago. He has also been a visiting researcher in University College London and in the Technical University of Creta in Greece. And today he's going to talk us about connected and automated driving and how to manage the intersections without signals, but also without centralized coordination. So without further ado, Claudio, thank you very much for being with us, and the floor is yours.
Thank you. Thank you very much for the introduction. And thank you again for hosting me during these couple of weeks in this Australian spring, Finnish autumn or winter. Anyway, so the goal of my talk is to talk a little bit about connected automated driving. I know that already quite some ongoing research around here, but I will just try to go through a couple of topics that we have investigated with some students of mine, and the idea is cover these 2 topics today, so signal for intersection and cooperative routing. So we'll just go briefly through the first part, a bit about why are we doing this and what is the motivation behind these couple of works I'm going to talk to you about, and then jumping into the two main topics of today. Now, we are of course talking about future mobility, and future mobility, of course, is going to be at least that's a forecast that there are going to be a lot of emerging technologies that will play a big role in how people are going to move around in cities and rural areas. One of them is, of course, connected automated vehicles. Now, there is a lot of promise around connected automated vehicles. The angle that I'm tackling here, and generally my research, is thinking how they're going to affect and impact our traffic and traffic management for our cities, road networks, etc. And of course, when we talk about connected automated vehicles, they basically have 2 main aspects where they're going to influence our systems. So one, thanks to advanced sensing and communication, they're going to be able to increment our sensing capabilities in our systems and communicate whatever they can perceive and sense with each other or with everything else. So this V2X idea. And the second part is that they can act as actuators. So that's the important part. They can affect in some way the traffic situation, traffic system, which may imply that system may behave differently from what we have seen up until now. And of course, these are the potential, but also resulting challenges. How we can actually manage the CAV traffic, so how we can optimize or steer their behavior to something more desirable. And this, for example, we may look at passenger comfort, energy consumption, or anything else that we may want to achieve as a goal. And in terms of coordination, so how actually these vehicles are going to interact with each other to improve the overall situation. And of course, in this dimension, there are a lot of problems to be solved in there about sensing capabilities and perception and safety issues and so on and so forth. But what we focus mostly in this talk is going to talk about integrating with traffic management that we're already doing nowadays. So how they're going to be positioned in that context. And then the issue of computational feasibility and scalability. Now, well, we'll dig a little bit later into this, but of course, thinking of solving a complete centralized problem for CAVs where everything is coordinated centrally is completely unrealistic and for sure impossible to happen for many, many reasons. Just to give a very, very quick overview about traffic management and how this is going to change over the years. If we think about traffic management today, the way it works, and that has been working basically for the last 50 years or so. We have a process which we try to manage, which is the transport system, basically a traffic system, which consists of conventional vehicle flow, so people driving their cars, bus drivers, and so on and so forth. We have some spot sensors of various kinds. Technology will evolve over the years, but the concept has been very, very simple. You put a sensor somewhere in your infrastructure, you place it there, it measures something. This could be, well, with various technologies, measure something. This goes to some traffic management center or some local controller, and there is typically wire communication. Now we're moving a bit wireless. But anyway, anything is computed in a central way. In many cases, sometimes there is some decentralized control, which is typically anyway for either for simple problems like isolated intersections, or for let's say emergency situation, or at best we do with hierarchical. So with some traffic management center deciding something, and then these decisions are diffused to the other layers, and decision is taken in basically in cascade. And the loop is closed basically through these actuators, which are nowadays traffic signals as the main ones. And then we have variable speed limits in motorways, for example. Message signs have been used for routing, and so on and so forth. But still, this is what has been happening up until now, again, with some technological improvement, but very much step by step. What we're going to expect in future traffic management systems is that this process, transport system, is going to be a system with enhanced capability vehicles. And the enhanced capabilities means that vehicles will be able to sensing the environment. They will be able to communicating whatever they sense to other vehicles, to infrastructure, to a signal, or to some other infrastructure-based detector, or to, well, anything else that can happen. They can alert your phone that they are passing by, or there is an emergency vehicle or something else. And actuators are going to be in vehicle as well. So in theory, and that's what we are working on, basically, what the broader research community is working on, well, vehicles can change their behavior based on some control decisions that are taken at some management level, at some traffic management level. They can adapt their speed, they can stop, or they can change their own routes, and other possible actions. And now the central computation that I said could be very problematic. The direction and the idea is that this calculation will happen massively decentralized way. So every basically vehicle is a computer, or maybe a collection of computers inside that can take certain decisions, and maybe exchanging these decisions through proper algorithms with other vehicles, they can agree on some consensus decisions. So the question when we are going to have this kind of a system is actually how we can how this is going to affect traffic flow efficiency, and in general, let's say sustainability, and how we can actually affect these implications. And so as I mentioned before, so if you look into literature, most of the works for CAVs, at least a couple of years ago, I would say the large majority of work were centralized. So the idea was that CAVs would exchange information to some central entity, and this central entity would calculate for all of them their control. And there has been a lot of works on intersection management, for example, where the rough idea was, okay, CAVs send their sensor information to the traffic signal or whatever intersection manager, and this would calculate the accelerations for all the vehicles. Solving this problem is computationally demanding. And another big weakness is that you have a single point of failure, meaning if something goes wrong, either in the communication or in the calculation optimization, then everything stops working, basically. Some works has been done about hierarchical or decentralized structures. So where you basically have a structure like this. So imagine here the dots are the vehicles. So where basically vehicles would, well, communicate to each other, maybe in clusters, or maybe talking to some specific part of the infrastructure, and then there is some other communication going on, and this could also be of various levels. And then the decision can be taken partly at these nodes, for example, partly centralized, and then exchange in various ways. This is a little bit of improvement with respect to the first one, to the purely centralized, but still would rely on this kind of hierarchy of decisions. So if something happens at an upper layer, this would cause a loss in performance, basically, on the lower layer. And almost none of the approaches are distributed. And by distributed, I mean that each and every node, meaning every vehicle, kind of tries to calculate and compute their solution and then exchange it with the others, and then trying to achieve what we can call consensus. It's called, like in robotics, for example, or anyway, some common decision making between vehicles. And basically, here is where we try to investigate how we can actually define strategies for CAVs so that we can achieve some level of distribution of this in the computation. Yeah, and well, we can look at this problem at different dimensions. Let's say that in this case, this is the more closest to vehicle level. You can think of optimizing vehicle trajectories on distributed level. I'm not going to talk about this today, even though we have some work. I'm going to focus on this upper level, so intersection management and network routing. With, of course, here there are many layers you can consider in this problem. So, going to the topic of distributed optimization. So the focus here is in what we call basically signal free intersection. So if you think of this evolution, let's say from nowadays regular vehicles, and then basically we have fixed time or actuated or adaptive signals. So this is where we are nowadays. So spot sensors, information gathered at traffic signal or some traffic management center level, and then implementing it into signals. Now, the more basically features connected automated vehicles are going to have, the more we go up in this ladder. And we can go to detector-free signal operations, so getting rid of sensors, and then we can go when there is automation to spatial temporal signal control, so control synchronized with movement of vehicles, and then we can think of readapt the infrastructure, like assigning lanes. But what we are going to talk here is mostly this idea of signal free intersection. It's not a new idea. So there has been papers back in mid 2000s, basically discussing of this idea in general. And the idea here is basically that you are in an environment where all vehicles are connected and automated, and they need basically to cross an intersection zone in the most efficient and safe way as possible. So you have this conflict area or intersection zone, and basically the idea is that vehicles need to adapt their own control commands, which could be, for example, acceleration, so that they occupy some dangerous areas one at a time, so they don't have any dangerous conflict happening. So there is quite some work on how this can be done with centralized control, basically controlling everything centralized. And again, here the idea is that every time you want to control, vehicles send their information to the signal or the signal, sorry, the intersection manager, and intersection manager calculates trajectories for all the vehicles, so that they then receive their own acceleration commands or speed commands. Now, when designing this, there are typically a couple of problems to be dealt with. First of all, agreeing on this crossing time schedule is a very, very complex problem. It's basically a combinatorial problem. So this is typically dealt with heuristics. So it's typically some heuristics determining the order of vehicles when they should cross an intersection and when the vehicle is supposed to cross an intersection of cars. So here we lose basically optimality by default. And typically in these approaches, there is an assumption that when the crossing speed at intersection is fixed and constant. And this is typically to simplify the optimization problem to be solved. And that's useful for designing some control methods, some management method, but not really realistic and not really necessary. So it's sometimes vehicles may have different desired speeds, or sometimes they have different maneuvers within an intersection that needs to may need to use different speeds. And another problem that some of these methods have is that the physical constraints typically depend on space, right? So it's like an infrastructure, an intersection is at a specific space location in the network, in the road, so a certain distance from a vehicle and so on and so forth. But typically most of the optimization solutions are highly depending on time. So you typically optimize over a certain time horizon, and you need to make some approximation. When is the vehicle actually going to reach the intersection? And then there again, you lose some degree of optimal solutions. And again, here, typically, this is done with some heuristics. So what we worked on to try to tackle some of these problems, at least. So we basically developed two methods. One is what we call a time scheduling distributed algorithm. And the second one is what we call a space-dependent optimization formulation. So the idea in the first of the two is that each CAV acts in a completely distributed way and calculates its own timing for crossing the intersection. And the idea there is that there is an exchange of information with neighboring CAVs, so with the other vehicles, but this information to be exchanged is very, very little. So, of course, any distributed algorithm implies exchanging this information. In many methods, not applied to this case, for example, but in some other cases for like, I've seen it, for example, for lane changing management or some motorway control management. The idea is to exchange, for example, the whole trajectory that the vehicle is supposing to do. But that would imply quite a lot of information exchange. Here we look into minimizing the amount of information exchange. Yeah, and the idea here is that, of course, in this algorithm, you don't have a single point of failure in the sense that each vehicle optimizes by itself the trajectory, or anyway, the driving behavior in approaching intersection. And this approach is computationally scalar, meaning that each vehicle solves a simple optimization problem, basically. And the computation doesn't grow as we have more and more vehicles. And then the second part, we work in this space-dependent formulation to mostly to overcome the second problem I mentioned over here. So this constraint of space. I will talk a bit. I will talk a little bit better later, but this would allow to avoid that heuristic need of defining the constraint of the optimization problem depending on the space, which is heuristically defined. Now, how this works, basically. So this time scheduling distributed algorithm is something, let's say, inspired from algorithms for scheduling tasks in robotic applications. So if you look into robotics, there is a lot of similar problems of basically synchronizing tasks so that one robot does a task immediately after another robot has finished the previous one. And of course, with different contexts, so we had to rethink a little bit how this can be done. But now there is some mathematics behind it. I will just give you a very intuitive interpretation of this. So imagine that you have an intersection, and that for now, let's just assume we have a single intersection, and this shared area should be basically occupied by CAVs, and each CAV basically at the beginning of the control period says that it will arrive at the intersection at a given time, and we also need a certain amount of time to be spent inside the intersection. So basically the idea is that the CAV would be able then to identify by, let's say, declaring the time at which it's arriving at the intersection, which are the other vehicles that will be in conflict with it within the intersection, and then exchange with these vehicles basically these arrival times. And then based on the overlaps that will be identified, basically the algorithm shifts by a certain delta in different directions the vehicle so that you can make space. So for example, in this case, CAV1 has enough space, CAV3 may have enough space, but CAV2 no. So in this case, basically it will move CAV1 to try to move earlier and CAV3 to move it later. Of course, these there are other vehicles, and these will be considered in the algorithm itself. And again, there is quite some math behind it. It's not only this, but this I think was the easiest way to represent it here. And so these algorithms run iteratively, basically certain number of iterations until basically it converges for each vehicle that is supposed to have these overlapping times. And this can be immediately promptly adapted whenever there are new vehicles entering. Again, it's plugged in basically. If there will be a CAV4, then it will be immediately integrated in the algorithm, because again, the algorithm is run by each vehicle individually. And so the idea is that here, after all this is run, at the end you have a sequence of vehicles crossing the intersection, and the entry and exit time in the intersection. Now, once you have these entry and exit times, what remains to do is basically to optimize the trajectory of this vehicle according to certain criteria that you may set. And then here, well, we did it a very standard, basically linear quadratic optimization problem, where we basically just consider a simple linear dynamics with some bounds on the speeds, acceleration, and speed and acceleration basically, and the two bounds x mean and x max are basically the time entering and exiting the intersection based on the solution of the previous distributed algorithm. And well, this problem is extremely simple. This problem is completely distributed, so each vehicle solves the problem by itself. So it's a very small optimization problem to be solved. So it can be solved with a blink of an eye, basically. And and so this would be in essence what the algorithm. Now this works quite well if you consider one intersection as a common basically shared space for all the vehicles to be. Now there's still a couple of problems to solve here. And one problem is what happens if you want to allow more vehicles inside the intersection. So imagine you have multiple lanes in intersections. No, what is supposed to show exactly like this. Anyway, you have multiple lanes in the, I think, if you have multiple lanes in intersection and multiple conflict areas in intersection, so with some vehicles with right turning, some vehicles with straight, and so on and so forth. Now, this the previous idea would work straightforward in a simpler case, or at least here, just allowing one vehicle intersection. But what if we want to allow more vehicles to be in the intersection? And so the idea basically here is to basically split the intersection into these zones, so quadrants of the intersection, and then the algorithm basically needs to add one loop around so that you actually consider all the overlapping only when this is in the predicted, when vehicles are predicting to overlap in time basically within each zone. So instead of looking at intersection just as one, so these algorithms scale linearly so that you just basically run one more basically loop of within the algorithm so that you just consider the zones where this overlap may actually occur. So if you are in this case, so before you would look at vehicle A and B, so they would have an intersection. In the second case, you would see that, for example, vehicle A and vehicle B would only overlap basically on that quadrant. So you just consider that one in your basically optimization. So the solution, if you are applying the original algorithm, basically from this situation, it would result in this case, where there is basically no overlap inside the whole intersection. But if we make this adaptation, considering different areas, then you just want to make sure that there is no overlap in the same area. And in this case, for example, you would save a certain amount of time, so the intersection would be more occupied by vehicles. And the second aspect we have been working on is about reshaping these lots. So as I said at the beginning, typically the speed inside the intersection is typically assumed to be constant, and which means that the time inside the intersection is also constant. This is not always desirable for various reasons, both because of the infrastructure reasons, but also because of trajectory planning reasons. For example, a vehicle had to decelerate in order to approach intersection, and so why making it accelerating again necessarily when, for example, there is no need of doing that. So this can be also handled in the algorithm basically by solving basically a relaxed version of the optimization problem. So instead of using hard constraints basically in the optimization problem where you just fix these two times of entering the intersection, you'd actually allow a small violation of the time slot constraints. And we also saw that basically by running this algorithm under certain condition, basically this violation will tend to zero. So it will shape in the optimal way also the duration of these steps. So instead of forcing them to be all of the same length, they will actually be allowed to be also of different length. So a few good features of this method is that here there are basically no coupling constraints in the optimization. So each vehicle can solve, each CAV can solve its own part of the problem. And the only interaction they have basically is in this distributed algorithm, which is anyway a linear algorithm in terms of performance. So it's still computationally efficient. So so this was the first part, this time dependent algorithm. Now there is still a little problem that I was mentioning, which is basically the fact that the predicted time entered the intersection has to be somehow, and the related constraints have to be somehow heuristically determined. Because the problem is time dependent. So you know when the vehicle is over time, but the intersection is, for example, 100 meters in front of my vehicle. You can of course estimate when this can happen depending on the solution of your problem, but it may not be 100% correct prediction for various reasons. So what we try to do is to reformulate the problem as a space-dependent optimization. So here you need just to rethink a little bit of how a dynamic system is basically formulated. And here, so basically the idea is that instead of calculating space as a function of time, we calculate time as a function of space. So this basically is a dynamic equation in space. So imagine space discretization and of your network, and this T basically says at which time are you in that specific point in space. Then the rest of the formulation is pretty much similar, with one little variation, which is the fact that you don't actually really have speed if you work in space formulation, but you have what we call pace, what is called pace, which is the inverse of speed. So that's basically what we try to control in this system. And if you want to try to minimize basically the efforts in controlling, so which is acceleration typically, related to comfort, energy consumption, etc., it's not easy to do with this formulation. So we basically define as a proxy for acceleration the difference in this pace. So how big is the difference in pace, therefore in speed, between two different time steps? And also here, well, we could demonstrate is an approximation of calculating basically the acceleration, or weighting actually the acceleration in optimization. But what is good in this approach is that basically you can basically define your constraints not anymore as you can define this constraint in terms of time entering the intersection, which is exactly what you solve basically from this problem. So without needing of converting this time to space and so on and so forth. So that would be basically a more exact formulation of the problem that you're trying to solve. And so this would allow better basically results as you have this one less heuristic step to be solved. One little problem is that this formulation does exhibit certain coupling constraints, but luckily there are algorithms that allow to solve this without this problem. So there is an approach in literature that is called distributed constant couple optimization via primal decomposition, and you can basically apply that and still solve the problem basically in a distributed way. Yeah, so this entering Lexington time can be obtained by optimization. A few results here of these methods. So we look at these basically case of one isolated basic intersection with a certain number of vehicles that are trying to enter the intersection, and then may have different behavior, basically different starting point, starting speed, and ending speed. So this is basically how it looks, the solution of the distributed algorithm for a sample of vehicles. Now just think that the y-axis is just a way to represent different vehicle IDs. So basically at the beginning you start with a situation like this, so where vehicles would like to be in the intersection, to spend the intersection a lot of times basically overlapping with each other. In this case, well, two bunches. Now here we plot everything from every possible leg all together in this figure. So just imagine this vehicle may be coming from all the different legs, and they want to be at the intersection at the same time. So by running iteratively the algorithm, basically at the end you end up in a situation like this. So where you typically occupy the whole available time in the intersection without conflict between the different vehicles. So yeah, so that shows basically the algorithm works and converge to a feasible solution. And now what I wanted to also show you a bit is how the two basically methods compare. So this is the time dependent algorithm, and this is the space dependent algorithm. So here I show for varying flows, so different demands. How is actually their performance in terms of time spent in the leg by the vehicles for the two algorithms? And what we can see is basically that SDA always results in lower time spent in the leg, which is travel time, basically, or time delay, however we want to call it. It's always performing better, basically, than the time-dependent formulation, which is what is typically used. And the reason is indeed the fact that there is these heuristic approximations to be done. And the other good feature of the SDA, space-dependent formulation, is that control actions are typically smoother than with the time-dependent optimization. And the reason here is both, both this approximation, but also the fact that in the time-dependent formulation, you may need to readapt the desired speed, basically with intersection also depending on the current speed of the vehicle. So basically, you may want to you have much stronger acceleration, so which is here in that algorithm with respect to these others, the space dependent. And yeah, so this basically was it about the intersection control. So I think I have 10 minutes to talk about this cooperative rerouting part. So here, the motivation is basically the same. So how we can actually decentralize or distribute certain calculations that are typically done in a centralized way. Now, what's the idea behind here? I guess most of you are familiar with the ideas of the fact that traffic naturally tries to evolve toward producer equilibrium conditions. So where all vehicles from the same OD are basically origin destination are experiencing travel time. And we know that this is not optimal from a system level perspective. And so we want basically one desirable, at least, state for our traffic network would be to get to what is called system optimum, so where actually the total travel time for all the vehicles is optimized. Now, there are studies about, quite many, about how to obtain this system optimum state. There is, well, not really good solution algorithm for that yet. It's a very, very complex computation problem. Of course, you can do it with lot of simplifications, but the centralized solution for system optimum for dynamic networks is not easy to achieve. But so what was our idea was actually, can we design a relatively simple distributed algorithm that would try at least to push the traffic system towards something that resembles it. This was our basically idea. And so here we thought, what if we just look at the redistributing flow at nodes, but routing at each and every node, in such a way that we try to avoid forming or deteriorating congestion at the subsequent nodes, links, in our route. So the idea is basically this routing is then implemented at intersection level. So each intersection is exchanging some information with the other intersections and then deciding for the routing of the vehicles approaching the intersection. Now, this will be not much different from having each vehicle routing, but there is just less information exchange in our mind. And yeah, so okay, this is what I was basically saying before. So what you see above is the idea of user equilibrium, below is system optimum. So and basically the idea is that when you put all together this should be better than this linear system. So, so the idea was basically try to design some sort of an algorithm that when traffic loads are not very high, maybe it's not necessary to go towards system optimum. So vehicles, if the load of vehicles in the network is not very high, vehicles can still follow whatever routing policy they would like to follow. And if networks start getting more congested, then you would try to push more towards optimum. And yeah, and so most of the approaches are indeed trying to calculate centralized system optimum over there. But so the idea here is that you perform this distributed optimization in each and every link of the network. And there is basically some communication between the vehicles and the intersection unit over here. And then intersection units can communicate with other intersection units. And of course, each intersection unit knows the destination of the CAVs that are coming. So the idea is that whenever, for example, a vehicle goes from the intersection, enters this link, so it will communicate with this intersection about its destination. This intersection unit would suggest which of the route, which following link should be taken for reaching this. And the basic assumption here is that each link is characterized by a fundamental diagram, and each link knows. Each intersection unit knows the fundamental diagram on each link, and then the current, basically, number of vehicles in each link is exchanged between intersection units. So the idea here is basically having this simple distributed routing algorithm. So where basically each intersection unit just keep tracks of vehicles, number of vehicles entering and exiting the links that approach the intersection. They would broadcast basically this information to the other intersection units, and they would receive similar information from the other intersection units. And then based on a modified, basically routing algorithm, shortest route for the CAVs, they would send the updated route to the CAV that just entered the link approaching that intersection. Now, how basically we approach that is via introducing a modified routing cost function in the following way. So basically, the idea is that to reformulate the total cost of the vehicle from, let's say, the following intersection to its destination would basically be the sum between this is the current travel time. So simply considering the current speed on the different links, plus basically these two additional terms. And you can see a representation over here of these different terms. So this is phi sigma, so which is this, well, maybe it's easier from here, the sigmoid function over here, and then a second function sigma tau, which is basically this other function, which is basically this other shape. So what this function basically say? This function basically say that if in a link there is no congestion, so if in this case these NCs critical number of vehicles or critical density. So if you are on not working, yeah. If you are on this part of the fundamental diagram, basically don't add anything to your functions. Don't do anything with your functions. And then start basically increasing the weight on that road according to to this sigmoid function that of course is a function to be calibrated so that basically you increase the impedance of a link as much as the link gets more and more congested. basically. And here it is, it's affected by this parameter, or that determines basically how skewed is this curve. And then we have a second term, which is basically a function that scales the effect of that curve, again, depending on another parameter. So it tells basically how important is this curve for your specific speed in your own. And the idea basically is this algorithm, this modified link cost function to be actually plugged in any shortest path algorithm. What we tested here is Dijkstra, but you can apply it with any other algorithm where there is basically a cost to go function. So just a few results here. So we did these experiments in using, well, another modified version of Suits false networks. I think that's a pretty standard network to test this kind of problems. So we basically defined just a short simulation here, just to demonstrate how it works, so half an hour, and with a high demand at the beginning, and then going low, so that congestion basically disappears throughout by the end of the simulation. And we assume here full compliance by CAVs, even though this is something, well, even though then we also tested how this would work when there is only percentage of vehicles following this routing. And well, baseline is all or nothing assignment. So if we just, so with all or nothing assignment here with this specific demand that we enter, so we see that the network gets highly congested. So here, well, a lot of the links are actually getting very congested. So some links reach the maximum occupancy, and this is the average occupancy in the network. So and this is the critical value. So anything well above this value means that the network is highly congested, and so this gets congested for a big part of time, and then well, only after demand basically falls, then the congestion disappears. And running our algorithm, so the first thing we can see is that well, traffic congestion are a bit far better. So the average occupancy goes actually quite lower. So this basically line here, so as compared to this line here. And also after basically demand drops, the congestion level also drops down very quickly, meaning the network empties very quickly. And also looking at the most congested links. So in the first case, the baseline case, you have some links getting fully congested basically for quite a long time. So here is hidden, but you can guess the point is somewhere here. And in this case, it drops much faster. These results basically improvement in the order of 13 to 26%, which is numerically kind of consistent with theoretical system optimal solutions. Now, of course, there is a lot of factors in there, but at least theoretical numbers match. Now, calculating system optimum again is not an easy nor feasible really problem for large scale networks. Now, what basically happens looking at links by links is that in certain cases, in this simulation, that's something that we are still fixing, or actually fix it, but I don't have the final results. So some links are getting very congested, and these basically links, as you can see here from the fundamental diagrams, are the very small links. So this is a problem actually of assignment in the network, which is also why some links get fully congested in the previous figure. So if you look at the behavior of more normal links, basically what this controller, what this algorithm does is to maintain the density or occupancy over here around the critical value, which is basically what you want to happen when you apply a controller for avoiding congestion. This is quite consistent in most of the common links, again, except from some little exceptions. There are, of course, some oscillations due to demand, but that's also normal behavior that happens in controllers. Yeah, and here, so if you look at fundamental diagrams, right? Okay, so for the links, at least with the high capacities, we see that the algorithm aims at operating at the critical density, which is, or at capacity, which is again a good property that is achieved. And then last thing that we looked into is these penetration rates. So what we could see is basically that the algorithm scales quite well with different penetration rates. So we start here, for example, with 100%, which was the result I was showing you before. So all vehicles connected, automated, and followed routing. But even if we start reducing this number of vehicles that use the algorithm, I would say up to 40–50% still, the algorithm is quite capable at maintaining around the occupancy around the critical value. And only if we go below 30% or something like that, then it starts to deteriorate and having higher congestion levels. And maybe I can skip the conclusions to leave some time for the questions. There is not much to add in there. And yeah, thank you very much for having me.
Thank you very much, Claudio, for the really interesting talk. Floor is open for your questions. No student wants to ask, yes. Thanks, David.
Okay, few things on the second presentation. You were talking about UE versus system optimal and saying that UE leads to fairness. And well, that may be true in a very, very short-term type of analysis. If you're going to do this over a whole network, then who cares? You know, you take a loss on this turn, but you get it back on the next one because you know you're going to have multiple opportunities. So shouldn't SO be the criteria?
Yeah, it could be. Yeah, thanks for your point. Yeah, that's definitely.
Can I comment something there? I know at least one paper that shows that when the congestion is very, very low, then the difference between user's equilibrium and system optimum is.
Well, when congestion is low, it doesn't matter.
Yeah,
granted,
exactly.
right. But when congestion is higher, then shouldn't we, certainly at this kind of level where every turn is a new optimization, essentially, shouldn't we be aiming for SO then? That's
that's the idea, to try to get something close to SO, but then how do you calculate SO?
Well, that's a different question. I mean,
the idea there is indeed that when we start getting congested, we aim for SO. When we are under congestion, then we try to get UE.
Well, it's the same, but I mean, it doesn't
really matter. Yeah,
and it's advisory, right? So this is something that you could have a mixed fleet of CAVs and non-CAVs, and this would still work. And the people who took your advice might have to give more harsh advice because some people would be ignoring the advice, but you would still be able to balance the system in principle.
That's the idea.
I don't know if there's a free rider effect for the people not taking your advice sneaking through, but that might be worth looking at.
That's something we are looking into.
All right. Now going back to your first paper, you had, I assume that was 100% CAV for that to work. So A, what happens if you don't have 100% CAV? You just can't do it, or is there some solution? And B, what happens if there's measurement error? Especially given that you have a decentralized system, and then the different vehicles will make different judgments about the state of the system.
So, well, for the first one, I think I'm not sure we can implement signal free if you don't have 100% penetration rates. I've seen some work in literature where they have some switching logic so that the signal works like the signal free if it detects there are only CAVs and then switches to traditional signal if there is some human driven vehicle. but as such, can't really picture signal for intersections with traditional vehicles present. I don't know, how do you see it, but.
And we've got a project where autonomous vehicles
Yeah.
could do that without the connectivity. But I don't think with human-driven vehicles, then that, I mean, that basically works as a yield sign. And which, you know, I mean, it works at low
Yeah.
enough volumes, but you know, when the traffic gets higher.
Yeah, exactly. I mean, it works. Low volumes is fine.
Yeah.
And second question is about these measurement errors. Of course, they may cause a deterioration. Measurement errors in whatever in whatever the solution. But again, the algorithm is fully distributed, so this deterioration would happen only for that specific vehicle. So I don't
But
think
if they chose to, if they measured and chose to go.
Yeah.
And the other vehicle measured and chose to go.
Yeah. So what you're saying is basically one vehicle predicts. So the problem here is when they predict their crossing time at intersection. So the problem you're basically saying is what if a vehicle wrongly predicts the arrival time at intersection, and while the algorithm basically identifies that there is no overlap, there is then actually an overlap happening because of measurement errors. The algorithm itself can't basically, at the moment is not designed to be robust for that. My practical intuition is that I believe that all these systems are anyway going to work with a control layer below that takes care of safety. I mean, I don't think that any of these trajectory planning algorithms can work without a, let's say, safety layer.
But what if the safety layer make it a deadlock?
What is the safety layer? So you mean that?
You have 2-3 cars that because of safety they stuck and stuck there forever.
Good question. I think that's a good question but in general, I think for designing all these cooperative coordinated algorithms, or even centralized. And I mean, I think this applies definitely for this work, but I think this applies for more or less any works in this field. That's not impossible.
Speaking of all the works in this field, where are the other modes?
Where are the other modes?
Particularly pedestrians.
With pedestrians, no, yeah, that's definitely a good point. In this part, definitely there are no, we didn't include them in intersection management, didn't include other modes. That's something definitely worth thinking. In the routing part, I think other modes can simply be incorporated within the delays in each link. So if you estimate there is going to be some time for pedestrians to cross or anything, that could be incorporated in that delay. That is it naturally doable. On the travel time within a link, the predicted travel time within a link can incorporate this time. So what we did in the other work, didn't show about obstacle avoidance, was actually to consider basically consider other type of users as possible obstacles that connected automated vehicles can or may need to avoid. But this indeed is not explicitly considered.
Considering the second paper, especially when you're thinking about equity, can you measure if some users or some origin destination pairs are having to sacrifice much more time than others?
We're looking into that now. That's definitely a big, well, it's a general big problem when talking about this. So we're looking into that. At the moment, probably there is some, of course there is, because otherwise that's implicit in the definition of a system optimum. My question is always, I mean, can you do it without? I mean,
Yeah, but the trade-off is
yeah,
if a couple of people has to sacrifice a lot for everybody else, then it's optimum with one objective function. But if you also consider somehow equity in your objective, it's not so great. If it's more evenly distributed, I mean, it's not going to be perfect, but of course there is
well, yeah, but what we are mostly looking is actually in this mixed traffic case. So who is actually that is sacrificing more time? I think the obvious answer would be the CAVs rather than the other users. So I would expect that CAVs are going to sacrifice. I mean, the less CAVs you have, the more CAVs are going to sacrifice in order to go towards system optimum. That's the intuition we have, and well, also some evidence from previous literature, but we are looking into this.
And for this paper, the only moment you use that they are CAVs is because they are compliant with the.
Yes.
Like if somebody were telling you a route and you were
Yes.
going to comply, it's also
But,
valid.
yeah.
That's because you're assuming the other drivers are UE. Right? So if the other drivers were much more stochastic,
Yeah,
not necessarily the case.
true. That's the point, yeah.
All right. For the second part, like, are people allowed to adjust their routes based on their idea during the travel, or the car will set the routes, or like adjust the routes based on the algorithm?
You mean the
Like, I mean, like, can
You-
human change the routes?
human drivers?
Yeah.
I think, no, I think in these simulations, the humans choose the route when they enter the network. Based
At the beginning part.
time, yeah,
Okay.
on the current travel time, but when they enter the network. So they don't adapt at each node, only CAVs adapted at each node.
So for your first paper, if I understand correctly, you first have a like for each conflict zone, you have like a spatial temporal pattern for them, and then you do the bottom layer control LQR for that for each individual vehicle, right? So I don't see how that makes it distributed, since you're still making the control over all vehicles. So isn't that still centralized?
So the algorithm is run,
Or
both the algorithm and the optimization is run by each vehicle independent. They
so you
just
only
change
consider
with each other those two resulting points. So the time when they enter, the time when they exit the conflict zone or zones. Then exchange with the other vehicles, and that's it. Then every vehicle optimizes.
do you consider only the preceding and following vehicle of that ego vehicle for, or are you considering all the vehicles?
So the idea is that vehicles broadcast these times to the surrounding vehicles, and then all vehicles that identify an overlap in these times are considered in the algorithm for each vehicle.
Okay, I see.
So when they all communicate together, then you reach at some point this.
So they have that time, like communicate between them, but they do control themselves.
Yes.
So in the result, you show that the initial solution and the final, is it like a iterative procedure, or they just one time communicate with each other, the interest time, just one time?
Iterative.
Iterative. So how long does it take to solve that problem, that example of 11 vehicles?
Computational is very, very quick. Because they just need
They're big or quick?
quick.
So if you have more, it's a streaming. I'm thinking that how really in real world is this scalable, because you are bounded by the slowest computational vehicle.
Yeah. But still, the computation is very, very fast in the sense that solving that whole algorithm, I mean, it's milliseconds or order of milliseconds. I mean, every time you solve it. So even if you need to run 100 times, it's a couple of if then send sequences and then solving that simple optimization problem.
I think we are good on time, so very much. They are open because most didn't have lunch before the seminar.
Okay, so you can keep this presentation, I think.